Hello students, welcome to the chemistry sessions. I hope you all are doing very well in your exams and in your class sessions. I hope you all have maintaining balance in between the physics, maths, chemistry and even biology. So you have to just go on maintaining the balance between all the subjects, and let's focus upon chemistry this time. We are discussing the optical isomerism. We are almost through with it. Let's take up certain questions related to it, and these questions now will not be having any kind of like a molecule that I have given to you, but something very different. I have got the statement questions. So question number 1 says benzaldehyde when treated with KCN. So benzaldehyde when treated with KCN will give certain kind of products. Some kind of a reaction will take place, and these kind of products, these are not separated by fractional distillation. So these products are not separated by fractional distillation. So here I have got my question. I have just formed the path of the question. What is the path? Benzaldehyde when treatment with KCN will give products, and these products are not separated, just be very careful while reading the statements. These are not separated by fractional distillation. Even the fractional distillation cannot separate these products. How will that be going to happen? So here in the case of benzaldehyde, what exactly benzaldehyde is, we have got the structure for it. A benzene attached with aldehyde group. So here I have got the benzene ring. It is attached with the aldehyde group. This is nothing but benzaldehyde. And how can I treat this benzaldehyde? I have to treat it with KCN. What will happen here in this case? A basic reaction will take place. I hope you must have got a slight idea about the reaction, and for those who haven't got it, I will explain step by step because we haven't taken general organic reactions yet. So here what will happen? I have got benzene and this aldehyde group. This aldehyde group will now act. How it will act? I am just expanding the structure first of all before making it react with KCN. So so this is how the aldehyde group looks like. Now what will happen here in this case? As you can see, carbon is less electronegative than oxygen. That means there are pi bonds over here. You can very well observe. So these are pi bonds, as well as I have got a sigma bond. Out of the two, which is more labile, which is more ready to shuffle? So pi bonds are weak. That means the electrons which are contained in these pi bonds are weak and can go anywhere, can shift very easily. So these pi bonds shift very easily. So that's why what will happen? The shifting will occur towards the higher electronegative atom. What is electronegativity? Electronegativity is whenever an atom is capable of attracting the electrons. So here oxygen is more electronegative than carbon. So I have got a slightly higher density of electrons over the oxygen as compared to the carbon atom. So there is a shifting. These pi bonds shift onto the oxygen atom. a delta negative charge develops. I am not writing just the negative, but delta. Delta represents slight, that means a little quantity. So over here it's little quantity of negative charge is there. So due to the shifting, due to the shuffling, what happens actually in organic molecules is the electrons are not stagnant onto the atoms, but they keep on shuffling in between each other. So that is the scenario. The electrons over here, the pi electrons are not stagnant, but they keep on shuffling between the two atoms. So one of the scenario is that the shuffle is occurring towards the electrons are moving towards the more electronegative atom. So here is the scenario that we are going to discuss. So over here it will be a delta negative charge developed, and onto the carbon due to the lesser electron density, because now the pi bonds have shifted onto the oxygen, what will happen? It will be having a delta positive charge. That means a little positivity has been developed onto the carbon atom. Now what will happen? Now comes the role play of the reagent which we have taken. This is an ionic compound. You all know what ionic compound is. It will dissociate into K plus and Cn negative. Now, out of K plus and Cn negative is the one which is going to react. For a simpler version, let me just have HCN instead of KCN. Like this. So in the case of hydrogen cyanide, this is nothing but hydrogen cyanide, this is ionic in nature. It will break into ions, positive and negative. Now the attack will take place. Whenever I am having a neutral molecule, any kind of a neutral molecule I can take, let us just say benzene I am taking, or any kind of thing. So what happens in the organic reactions is, the neutral molecule is this, and there is some kind of shuffling of electrons going on every time in the neutral molecule as well. So what happens whenever I am trying to make it react with something, any kind of, let's say, ionic compound I have taken. Why ionic compound? Because even in ionic compound I have got positive and negative charges which can interact with the positive and negative charges developed over here. So there may be an interaction possible. So that is why I have made it react with HCN here in this case. So what will happen? The Cn negative will shift on towards the carbon which is positive. So Cn negative group can attack onto the carbon. The negative charge will attract the positive will attract the negative, and vice versa. Here positive will going to attract oxygen. It will going to attack the oxygen here in this case. What will happen? I am not now drawing, I am just mentioning it as C6H5. Now the carbon is having Cn like this. What do I get over here? Here I have got, this is a very simple reaction. What is happening here? The cyanide is attacking the Cn negative, the cyanide ion is attacking onto the positive carbocation, the carbon atom, which has the slight delta positive charge. I hope you all are getting it. And the H positive is attacking onto the oxygen atom because it has got negative charges. So here what we have got, carbon with Cn, oxygen now got attached with the hydrogen. I have got OH group and one H. So can you see a chirality over here? This is the basis of our question. Why I have given you such a question? Because this is related to chirality. The question was that whenever the benzaldehyde was made to react with KCN, let's say if I make it as HCN, that would be simpler for you. So what will happen? It will give some products, and the product will be what kind? Will not be separated by fractional distillation. So actually what happens in fractional distillation, we boil certain compounds, we have got a mixture of compounds, we have to separate each and every compound. What happens? Whenever I try to boil that mixture, the compound having a lower boiling point will boil off first, it is now separated. Then comes the turn for the next compound. So it seems to be a bit, confusing, but it is actually very simple. So that is how the kind of questions which come up in the IIT mains. So you need not to worry about that, we are going to solve it. The absolute configuration of this very molecule we need to find out. Just as what we did in the case of isomerism, in the case of assigning the RS configurations for the simple molecules, that means having only one chiral carbon, that is the only type of the procedure over here. You need to just find out the number of chiral carbons, that is the first step, and then you just assign the configurations with the same kind of procedure, with the same rules that we have followed. So let's just take up the example here. There is COOH, OH, Cl, CH3. So these are the groups, these are the different kinds of groups which are attached. So what are the chiral carbons? Here we have got 2 chiral carbons. That means number 1, this very carbon is actually attached with 4 different groups. I mean to say that this very group will be treated as a whole as one. That means I have got 4 attachments different. Again, if I look on to this very carbon, here I have got again 1, 2, 3 different along with the 4th one. So that is what the 4th one is. That means 2 different kind of chiral carbons here over here. So let me just mark out the chiral carbons here. These are the 2 chiral carbons that we have got. Now there is a very simple method. Again we need to assign the configurations. So as per the priority order, as what we have did earlier, so what will be the priority order? It would be as per the atomic mass or atomic number. So in the case of, as I told you, the priority orders so for the molecules, I need to have either atomic on the basis of atomic mass or on the basis of atomic number. So in the case of isotopes, we need to consider the atomic mass because the isotopes are different, are having different kinds of neutrons. So the atomic mass will be different in the case of isotopes, whereas in the case of normal molecules, normal elements, atomic number always differ. That is, the number of electrons are always different. But that's not the case in the case of isotopes. Isotopes have got the similar kind of electrons. So that is what we have discussed. So this was considered in the terms of isotopes if we are discussing. And this is for the general elements. So I need to consider on the basis of atomic number. So that is how we are going to assign the priorities over here. So COOH, OH. So if I try to consider all the 4 groups, which will be the number 1? The number 1 will be, let me just compare the first atoms. So the first atoms, if I go this ways, if I go this ways, and if I go this ways. So in the case of first, comparing the first very atoms, I have got oxygen here, I have got a carbon, and here as well I have got a carbon. So oxygen will be on the higher priority. That means number 1 to be assigned to this very group. So let's move on to now the 2 carbons, 2 remaining carbons. I need to assign the priorities between the 2. So if I move on to this very carbon and this very carbon, similar kind of atoms. But if I move on to the next, so on to the next, what do I have? So if I move next here, as we all know that COOH, this is nothing but the carboxylic group, and it must be treated as a carbon attached to oxygen, an oxygen attached to a carbon. So that is how we are going to deal with the C double bond O as we have discussed earlier, and finally the OH. Now the first very carbons are of similar types. Next atom would be the oxygen as per the treatment. But over here if you look, the next atom is chlorine, that means higher side, that means the priority. Chlorine is always on the priority, it has got higher atomic number as compared to the oxygen over here. So I hope you all have got it that this very group over here, this whole group which is treated as one group attached to the carbon atom, this very carbon atom, it must be treated as 2. So that is 2, and for this naturally it will be 3. So what do I have? 1, 2 and 3. So that is how we are going in this case. So let me just draw this very curve again. Okay now. So it's 2 already. So 1, 2, 3. So that is how we are going to have a curve. That means clockwise direction R. But if you notice, the hydrogen is on the horizontal. So you need to invert the configuration as we did before. So instead of R, it would be S. So that is for the carbon number. If I try to have a proper chain, if I try to have a proper numbering of the carbons during the formation of the word root, so I will be numbering the carboxylic acid carbon as 1 and followed by 2. So I have 1, 2, 3 and 4. That is how we are going to number the carbons. So on to the 2 I have got S. So can you see any kind of options? Yes, I have got 2 options showing 2S. So that means I have eliminated the 2 possibilities. Let's just move on to the next. So here if I consider this very carbon, chlorine, C and these very groups. So out of all, definitely the chlorine will be on the higher side, will be on the priority 1. Now comparing this carbon and these very groups. So carbon, carbon, if I move here like that, so the carbon, carbon would be similar kind. Let's move on to the next atom. So the next atom would be oxygen, but over here there is no kind of next atom. That means this very group again will be on the higher side, that means 2 to assign this group and number 3 to this, 1, 2, 3. So that is how we are going to have, that is anti-clockwise direction means S, but over here the hydrogen is on the horizontal. So again what we are getting is the inverted configuration, that is R. So we get R and the carbon number is 3rd, so 3R. Is there any kind of option? Definitely yes, A is the answer. So I hope you all have got the answer over here. So that is how we are going to assign the different kind of configurations, different kind of RS configurations to our complicated molecules having more than 1 chiral carbons. So I hope you all have got the idea. Let's move on to the next very question. So let me just rub this off. A very simple question this is. So the number of stereoisomers obtained by the bromination of trans-2-butene. So I need to brominate what? Trans-2-butene. So that is, I need to have a bromination of this very compound. So in the case of bromination, what is the product? So I need to brominate this. Bromination in the presence of what? In the presence of, I can say, the sunlight. So that is how it is going to be. Or they haven't mentioned about what kind of a bromination are they performing. So we are considering the simple bromination. So over here, I need to have the number of isomers. So first of all, just try to form the product out of it, try to form the product of the bromination, and then we will get our answer. So over here if you see, what is bromination? I need to brominate, that means this very double bond. If I try to consider the free radical mechanism, so we are considering the free radical, what do we get? Twice of Br free radical we get, that is all we know. And over here as well we get 2 free radicals. That means something like this. So that is how we are getting the radicals. So either the bromine gets attached here or the bromine gets attached here. So these are the only possibilities. If the bromine got attached here, I get what? I get something like this. And if the other bromine again comes up onto this very free radical, what do I get? A dibromo product we get. And as per the stereochemistry, if you consider, it would be definitely this very stereochemistry. That means it must be an anti-product. So, I would like to discuss one more reaction over here if I am not considering the free radical mechanism but the bromination in the presence of CCl4. That is what we have done under the category of test for unsaturation. So, this is test for unsaturation. So, in this very thing, we always get what kind of a product? We always get which of the following pairs are not position isomers. So, it is a basic isomer type question, that means included in structural isomerism. So, I need to find out which are not position isomers. So, what are basically position isomers? So, position isomers are those which are having same molecular formula but different positions of functional groups or the double or triple bonds which are included in the molecules. So, it is different position of double or triple bonds, or I can say again the different positions of functional groups, but what remains the same is the same molecular formula. That is the only criteria for each and every isomerism. So, let us just now move on to the options. Option number 1, what do we have? These two molecules. So, if you look over here, the position for this O, what is this group? This is the functional group, that is ether. And if you look over here, I have got carboxylic. Here this is carboxylic. Now in the first case, you can notice that the position of the oxygen here, that means it is starting off with the methyl, then we are going on to the oxygen, starting off with the methyl and going on to the oxygen. So, this very position for this functional group is completely fixed if you see, whereas where are the changes actually? Changes are going on within the chains. That means it is not the position isomer, but what kind of an isomer? It is chain isomer. Now, if I move on to this very part, COOH, COOH. So, earlier the COOH was onto the very first carbon, but the rest of the chain was N 1, 2, 3, N propane. But if you see over here, now the structure has been changed and even the position of this functional group has been changed. So, I hope you are able to notice it. Now, if I move on to the next two options, what are the next two options? Okay. So, the first option over here, that is the C. C is having again 2O, these are nothing but the functional groups, again 2O functional groups. So, the position of the functional groups is again changed, showing what? Position isomer. So, that is also position isomer. Why? Because over here there were only one carbon atom between the oxygens, here I have got two carbon atoms, but still the molecular formula is same. Now what I got? Just like the carboxylic acid one, we have got OH here and now the position of the OH has been changed, but still the molecular formula is same. So again this is what? Again this is position isomer. So if I look at the options, all of the options, what do I get? Here I have got two position isomers again, and in the previous one I have got again this is position, but this is not, because here the position of this oxygen has not been changed at all, the remaining chain has changed. That means this is chain isomer, not the position. I've got the answer. I needed to find out not position isomer. So that is this very case. I hope everybody has got the answer here. Now let's move on to the next question. What do I have next? Identify the correct statement. So you need to find out the correct statement. Dimethyl ether and ethanol are chain isomers. So let us just draw the structures for that. So what is dimethyl ether? It is this. And what? Ethanol. So over here, if you see, the molecular formula is same. It is C2H6O, C2H6O. But what is the difference over here? The type of functional group. So this is not chain isomer but functional isomers. So it is functional isomerism. I hope you all are able to recall the definitions for each and every type of isomerism. Now, ethanoic acid and methyl methanoate are position isomers. So what is ethanoic acid? So ethanoic acid is this. What is methyl methanoate? That is methyl methanoate. Again what? Again I have got similar kind of molecular formula, that is C2H4O2, C2H4O2 in both of the cases. But what is differing is the type of functional group. Again what it is? It is functional isomerism. Again this is functional. Now if I look on to N-butane and isobutane, they are saying N-butane and isobutane are functional isomers. So let us just see. I've got N-butane, that is this. And isobutane. That is isobutane. N-butane and isobutane are functional isomers. Is it so? If you see, the chain has been changing. So it is nothing but the chain isomers, not the functional. Because here there is no kind of a functional group or a double bond present, double or a triple. So this is chain isomers. Now if I see over here propane 1-ol and propane 2-ol. Propane 1-ol is what? It is okay, here I have made propane 2-ol, and what about propane 1-ol present on the first carbon? That means this. Here if you see, not the type of functional group is changed, that means this is not functional isomerism. Here the carbon chain is none of our concern, the carbon chain is remaining as it is. What is changing is the position of this functional group. That means this very statement is correct. These are nothing but the position isomers. I hope everybody has got the answer. You need to analyze each and every option given in the question very accurately. So D is the answer. Now let's move on to the next question. The type of isomerism observed in urea molecule. So let us just draw the structure and need to see what type of isomerism is actually shown by urea. So that is nothing but the urea molecule. What kind of an isomerism will that be? Can I change the functional group? No, I cannot. Because if I need to change the functional group, make it somewhat terminal, let's say that this very functional group, I change it into CHO. then how will I complete the entire chain? I have got only nitrogens left. So there won't be same molecular formula. So that is why it is not a chain isomerism. It cannot be a position isomerism. It cannot be a functional isomerism. So what it would be? It is nothing but the tautomerism here. So it depicts the tautomerism. So how does it shows the tautomerism? Let us just draw the tautomer. This hydrogen will be acidic and will be attracted towards this oxygen. And how will I get the form? It will be like this. So it is amido form and this is imidol. Amido and imidol. Instead of keto-enol, in the case of urea, I name it as amido and imidol. I hope everybody has got it. This is nothing but the tautomerism. So that is tautomerism, and finally we have got it answer, that is D over here, not chain, not position, non-geometrical, but tautomerism. So let's move on to the next one. What do I have? Next question says, which one of the following compounds cannot show tautomerism? So as I said, I will be covering mostly questions from the topic tautomerism. It is mostly repeated topic. So let's now check out which of the following compounds cannot show. You need to be very careful while reading the question. Cannot show tautomerism. So let us just observe. For the tautomerism, what is the condition? The condition number 1 for tautomerism is you need to have alpha hydrogens which are acidic. Also, alpha hydrogen must be attached to that carbon, or I can say to the carbon which is unsaturated, to the saturated carbon. So if you observe over here, I have taken up 5 options, not a typically a pattern of JEE Advanced, but I have taken it the 5th option in order to increase the level of difficulty. So here I need to find out that compound which cannot show the tautomerism. So you need to find out the alpha hydrogens, that too acidic, and that too connected with a carbon which is saturated. That means having no kind of double or triple bonds. So that is our main aim. In the very first acetone, we have got so many alpha hydrogens, if you see over here. Now in the B part, if you observe this very carefully, this is the enol form of this ketone. That means definitely it is a tautomer itself. It is the enol form itself. That means it can undergo tautomerism. Now let's move on to the C part. What do I have? In the C part, again if you observe, this very part does not have any alpha hydrogen, but over here I have got 2 alpha hydrogens. Clear? In the D, what is there? So in D, there is 1 hydrogen here, that is alpha hydrogen. But if you look very carefully, the carbon onto which it is attached is unsaturated, having a double bond. That means this cannot show tautomerism. Cannot show tautomerism. That means I am left with option number E. Again it has got 1 alpha hydrogen and 2 more alpha hydrogens. So I hope everybody has got the answer. The answer here is D. A very simple question, you need to have the concepts right. So let's move on to the very next question. So the next question says, Okay, I need to find the maximum enol content. What is enol? That is again a tautomer of the keto form. So let us just draw very basic keto-enol form here. So I am taking up acetone in this case. I need to do is what? To create an enol form. So the enol form will be this. So that is keto, that is enol.